Learn like a pro.
When we talk about power, we usually think about the total amount of energy something has. But what if I told you that's only half the story? The real key to understanding how our world actually works, it isn't just about how much energy we have, but how fast we can use it. That speed, that rate of transfer, well, that's what truly defines power. So, in this explainer, we're going to go on a journey from the super small to the massive. We'll start with the basic idea of energy speed, learn how to measure in watts, and then see how different resources deliver their power. We'll even calculate our very own power output before we zoom out to look at the entire global energy balance sheet. Let's get into it.
Okay, first things first, let's build a really solid gut feeling for what power actually is. Forget the formulas for just a second, and let's think about a simple comparison to really get the core idea.
Seriously, think about it for a second. A regular car battery, it holds a pretty decent amount of energy, right? Enough to start your car over and over again. A lightning strike, on the other hand, it's over in a literal flash. So which one really packs more of a punch? Well, the answer is the lightning strike, and it's not even close. This slide shows you exactly why. While a battery holds a good chunk of energy, it releases it kind of slowly, through a narrow little pathway. A lightning strike unleashes all of its energy almost instantly through a massive channel. That incredible speed of transfer, that is what we call power. Okay, so we've got the concept down, but how do we actually put a number on the speed, right? How do we measure the difference between a tiny trickle and an absolute flood of energy? So here's the more formal definition. Power is simply the rate, the speed, at which energy is used or moved from one place to another. You can think of it as the how fast factor that connects three huge ideas: the energy you have, the work you're doing, and how much time it takes to get it done. And this shows the relationship perfectly. This power gauge is like a speedometer for energy. It's just measuring the flow. And the formula? It's beautifully simple. Power equals the energy used, or the work done, divided by the time it took. And the standard unit we use to measure all of this is the watt. So here's the crucial thing to remember. It's this direct relationship. If you see something that's rated at 1 watt, it just means it's using or transferring 1 joule of energy every single second. This is the fundamental building block for literally everything else we're about to talk about. So now that we've got that basic unit down, let's scale this thing way up and see how it applies to the massive systems that power our entire civilization. Every single way we generate energy, whether it's burning coal or capturing sunlight, is basically a giant engine that's designed to transfer energy. And each one of these engines has its own unique power signature, which is defined by things like how reliable it is, how much it costs, and, of course, its impact on the planet. Now, at the highest level, you can really split our energy resources into 2 main camps. On one side, you've got renewables, the stuff that's naturally replenished. And on the other side, you've got non-renewables, the things we have a fixed, finite supply of. And believe me, this one distinction drives pretty much all of our global energy policy and debate. So when we look at our chemical and nuclear options, we see this classic trade-off, right? Fossil fuels, they've been the backbone of our economy because they're reliable and for a long time cheap, but the environmental cost is huge. Nuclear offers just incredible power with fewer greenhouse gases, but then we're left with the challenge of it being non-renewable and, of course, the waste. Even biofuels, which are renewable, come with their own pollution problems. There are just no easy answers here. Then you've got the other side of the ledger, the forces of nature. Wind and solar are amazing. They're clean, they're renewable, but their biggest challenge is consistency, what engineers call intermittency. They only work when the sun is shining or the wind is blowing. Hydropower is more consistent for sure, but building massive dams has its own pretty significant environmental and financial costs. And geothermal, it's a fantastic, clean resource, but it's only available in certain places. So with every option, we're forced to weigh a different set of pros and cons. Okay, so we've talked about lightning strikes and global power grids, but all this physics applies directly to you right now. So let's make this personal. Let's actually calculate the power of a simple, everyday action. Let's take the example of a 60-kilogram person climbing a 3-meter flight of stairs in about 10 seconds. Okay, so step 1, we calculate their weight. That's just their mass times gravity, which is about 600 newtons. Step 2, we figure out the work done against gravity. We multiply that weight by the height, which gives us 1,800 joules of energy transferred. And finally, we just apply our power formula. We take those 1,800 joules, we divide it by the 10 seconds it took, and what do we get? 180 watts. That's the power output of an average person jogging up a flight of stairs. It's the same measurement we use for a light bulb, but in this case, you are the engine. Pretty cool, huh? All right, for our final section, let's take that simple 180-watt calculation and just zoom all the way out, because the exact same logic, it applies to our entire planet. This slide just connects everything brilliantly in what you could call the energy economy framework. Over on the left, you've got the source, the sun, wind, fossil fuels, whatever. In the middle, you have the process of converting that raw energy, which always has some loss. And then on the right, you get the final output, the useful power that actually runs our world. The physics is exactly the same as climbing the stairs. It's just happening on an absolutely unbelievable scale. And so that brings us to the ultimate question. The physics is clear. The resources, we know what they are. As our global demand for power just keeps going up and up, the real challenge for all of us is deciding which of these resources we're going to rely on and what trade-offs we're willing to make to balance this global energy ledger. What's the right mix? That's the critical question we all have to face.